Let us start the lecture. In this lecture, we are going to discuss about AC circuit containing resistor and capacitor. We already discussed about the AC circuit containing only resistor, only capacitor, and only inductor. And we also did the phasor diagram also. In this lecture, we are going to discuss about the if we have a resistor and a capacitor in a AC circuit, then how we can find the EMF current. Yes, just see here. As we know, we have the EMF is our E equal to E naught sin omega t. Yes or no? Here you can write also. After then, as here resistor and capacitors are connected in series, so same current is flows through both resistor and capacitor. We can denote just like this. In R, current led goes from left to right in this direction, I, and capacitor also current goes from left to right, that is I. Yes or no? Then the potential drop across the resistor becomes, we can write potential drop as VR here. VR becomes V, as you know from Ohm's law, V equal to IR. So here you can write I into R, or we can write the maximum or a peak potential drop E naught R, which can be written as I naught into R. Yes or no? Similarly, we can write the potential drop across capacitor is, we can write VC. VC can be written as I. Here we have to write the opposition offered by the capacitor, and you know that is XC. Yes or no? Capacitive reactance. Or here you can also write the maximum potential drop across capacitor. We can denote that as V naught C. V naught C becomes V naught XC. Yes or no? Then you have the phasor diagram here. As you know, for resistor, there is no phase lag between the current and EMF. So here you can show the phasor just like this. The direction of I and direction of VR is same. Okay, but in capacitor, we know in capacitor current lead EMF by phase pi by 2. Yes or no? So for capacitor, here you can say current lead EMF by phase pi by 2. That means we can also say EMF lag behind the current by phase pi by 2. So here VC can be written just like this. These are pi by 2. Yes or no? We'll draw this as phasor. In phasor diagram, we can represent this as let our VR, which makes angle omega t with the x-axis, and you know for resistor, I and VR along same line. Represent I on this also. So, as we know, same current for the capacitor. So for VC, we can draw the phasor just below the current. These are VC. Okay. This angle is our omega t, and you know this angle is 90 degree. Then as here you can see our VR vector is along this direction and VC vector is along this direction, then our resultant vector goes through this direction. Yes or no? Here we can obtain our E. Here we have to use the parallelogram law of vector addition. You can see here E can go through this direction. This is our EMF E. Okay. And how you can represent this? We can write E as under root cos 90 degree. As we know, the angle between VR and VC is 90. So here we have to write 90 degree. Okay. And then this cos 90 is our 0. So we can write E vector or E as under root VR square plus VC square. Yes or no? For maximum drop, we can write E naught is equal to under root, in place of VR we can write V naught R square, and in place of VC you can write V naught C square. In place of V naught R we can write I naught R. Here we have in place of V naught R we can write I naught R, and in place of V naught C we can write I naught XC. Yes or no? Just write on that one. Here you can see I naught R square plus I naught XC square. Yes or no? Then how can we solve it? or squaring the above term, we can write I naught square r square plus I naught square x square. From this we can take I naught square common, so no. Then as we know, the square root of I naught square is equal to I naught. So hence here you can get I naught under root r square plus x square. Hence our I naught, hence our I naught becomes E naught by r square plus x square. As we know from Ohm's law, I equal to E by R, where R is our resistance, that is the opposition offered by the conductor. Here we get I naught is our E naught upon under root r square plus x square. R square plus x square means here net opposition offered by the resistor and capacitor. Here you can say this is our impedance also. This is our impedance, or you can write Z also. This is the here this is the opposition offered by series RC circuit. This is all over the AC circuit containing resistance and capacitance. Here you can see, here we have I and here we have E. We can obtain that our EMF E lag behind the current in the RC circuit. In RC circuit we can write that EMF lag behind current, or we can write current lead EMF. Okay. Then we have AC circuit containing resistor and inductor. Here also R and L are connected in series, and hence we can say the same current flows through both R and L. Here we have to give in our input AC is our inert sine omega t. We give the input equal to inert sine omega t. Then as you know, R and L are connected in series, so here the direction of current is same for both R and L, yes or no? In resistor current flows from left to right, in inductor also current flows from left to right. Then the potential drop across the resistor can be written as you know from Ohm's law V equal to IR, so here you can write VR is equal to current flows through the resistor and resistance R. Then the maximum potential drop across resistor can be written as V naught R. V naught R can be written as I naught R, because I naught is the maximum current flows through the resistance R. Okay. Then we have to write the potential drop across inductor. Here for inductor we can write potential drop is our VL, and this VL can be written as I into XL. As we know, the inductive reactance is our XL, that is the opposition offered by the inductor to the flow of charge. And then for maximum drop across the potential inductor, we can write V naught L. V naught L can be written as I naught XL. Then have a look at the phasor. Let us see here. As you know, in resistor we have the EMF and current are in same phase, so there is no phase lag between them. Then we can draw the phasor for R is just like this. Here is a VR. Okay. So as VR and I are in same direction, so here we draw a phasor just like this. Okay. Let this represent our VR, and I is also on this. Then as we know, the same current flows through the inductor in the same direction. So as in the phasor of inductor, we know current lag behind the EMF by phase pi by 2, or we can also say EMF lead current by phase pi by 2. As we have I here, that means current is here, so here we have to draw a EMF which is lead the current. That means here we have to draw the EMF just like this, or you can say potential drop just like this. This is our VL which lead current I. So how you can represent this in phasor? Just see here. Here we have I, so you have to draw VL is along this direction which lead the current by phase pi by 2. So You just draw here, and this is our VL. Okay. And the net resultant, as we can see, VR is along this direction and VL is along this direction. So our resultant EMF can draw along this direction in between VL and VR. Yes or no? So we can write, or we can draw E along this direction. This is our E. Yes or no? Here we have to use the parallelogram law of vector addition. Yes or no? Here you can see E can be written as under root E resultant EMF under root VR square plus VL square plus 2 VR VL cos 90. Yes or no? As the angle between VL and VR is 90. As we know, cos 90 is at 0, so we can write this as VR square plus VL square. Yes or no? VR square plus VL square. For maximum potential drop, we can write E naught in place of E and V naught R in place of VR and V naught L in place of VL. So just write down. In place of V naught R, we can write I naught R, and in place of V naught L, we can write I naught XL, as we discussed before. So by solving this, we can get E naught is our I naught under root R square plus XL square. So our I naught becomes, so here you can see I naught becomes I naught is equal to E naught by under root R square plus XL square, and here the impedance, or you can say the resistance offered by the, or opposition offered by the series RL circuit is R under root R square plus XL square. From the phasor we can obtain that. You see here, here we have I, and here we have resultant EMF E, and you can see that here EMF lead the current. Yes or no? EMF lead current in series RL circuit. Here you can say EMF lead current, or we can also write that current lag behind EMF. Then we have the main circuit, that is our series LCR circuit. This is very important, and that is our long question also. Then the final one is our AC circuit containing inductor, capacitor and resistor. That means here in this circuit, here we have the three circuit elements: inductor, capacitor and resistor, and all are connected in series. As we know, if the circuit elements are connected in series, then the same current flows through both inductor, capacitor and resistor. Yes or no? So then just draw that one. Okay, you see, just draw current for inductor. In inductor, current flows from left to right, left to right. This is the right, and capacitor also left to right, and for resistor also current flows from left to right. Okay, this is the direction of current through inductor, capacitor and resistor. First come from resistor. As you know, in resistor there is no phase lag between the potential and current. So the potential drop across resistor is along the same direction of current. We can draw the potential drop across resistor as, this is a VR. There is no phase lag between the I and VR, as both are comes from left to right. That is the same direction. Yes or no? But in capacitor, we know, in capacitor current lead EMF by phase pi by 2. That means here you can say also EMF lag behind the current. Yes or no? So as we have current here, so here we have to draw the EMF line just below the current. This line is our VC. Okay. For inductor, we know current lag behind EMF by phase pi by 2, or you can also write EMF lead current by phase pi by 2. That means here we have to draw the EMF, that the potential drop VL is just above the current, and which makes angle pi by 2 with the current. Yes or no? So how can you draw there? This is our VL. Yes or no? Input is our inner sinusoid. First of all, we have to write the potential drop across resistor. The potential drop across resistor can be written as VR is our IR is on. So maximum or peak potential drop can be written as V naught R equal to I naught R. Yes on. So then the potential drop across capacitor. VC equal to IXC, or the peak potential drop can be written as V naught C equal to I naught XC. Similarly, potential drop across inductor can be written as VL equal to IXL, or then we have to write the potential or peak potential drop across inductor can be written as V naught L. This can be written as V naught L equal to I naught XL. Yes, all. Then we have to draw the phasor diagram. Let this is the VR, and we know the current is also on this direction. Then for capacitor, we know EMF lag current. So for capacitor VC line or fourth quadrant. This is our VC, and we know for inductor EMF lead current by phase pi by 2. That means here the as current is in our quadrant 1, so our potential drop across inductor VL must be in quadrant 2. And just listen, that must be opposite to VC. This is our VL. Okay. Here, if we consider the potential drop across inductor is greater than potential drop across capacitor. So here let's assume VL greater than VC. If we assume VL is greater than VC, so the net potential between VL and VC is along the VL direction as VL is greater. Yes or no? So how we can represent that? We can write VL minus VC along this direction. Along this direction. Yes or no? Then here we have two vector. One is our VL minus VC and another is our VR. So our EMF or net EMF is along in between VL and VL minus VC and VR. Yes or no? So along this direction E can be drawn. So how you can find the impedance here? Here also you have to use the parallelogram formula. One vector is our VR. Remember, one vector is our VR and another vector is our VL minus VT. Not only VL or not only VC. Here you assume VL is greater than VC, or you can assume VC is greater than VL also. Yes or no? If you assume VL is greater than VC, then our EMF lead current. Yes or no? If you assume VC which is greater than VL, then our EMF is along this direction and that lag behind the current. Yes or no? Then how you can use the parallelogram law here? Just see here. The net EMF is for VL minus VC and VR. So here you can write under root VR square plus VL minus VC square plus 2 VR VL minus VC cos 90. So no? As you know, cos 90 is our 0. So this can be written as, yes or no, under root VR square plus VL minus VC square. Here also we have to calculate the peak potential drop. So here we have to write E naught, and that can be written as E naught can be written as under root V naught square V naught R square plus V naught L minus V naught C square. In place of V naught R we can write, here we have, in place of V naught R we can write I naught R. In place of V naught C we can write I naught XC. In place of V naught L we can write I naught XL. Yes or no? Then just put that on and we have to find the impedance. Hence, E naught can be written as under root I naught r square plus I naught xl minus I naught x square. So here you can take I naught square common, or I naught becomes E naught upon under root r square plus xl minus xc whole square. Listen, here the denominator term is our impedance, that is the net the net opposition offered by the series LCR circuit. This is all about the lecture. In the next lecture, we can discuss about the resonant frequency and impedance triangle of LCR series circuit.